Okay, here we are. One more lesson to go through, 11.3 this time, called Measuring the Properties of Simple Circuits. This YouTube link I've put in my electricity list down here, and then with the little in the description, should be able to see which section of the textbook corresponds to each video. Make it nice and clear for you. Notice that we're not doing a PowerPoint, we're doing yet another um, Word doc here. Maybe I can make it a bit bigger with some less stuff on the way, a bit easier to see as we go through. So I'm going to go through this one maybe a bit faster. Probably be best if you went through it on your own time or check out the YouTube video, ask me any questions. I'm probably going to have to make a lot of supplemental material for these next few lessons. So just keep an eye out for those in case they're not coming out at the same time. But basically, we have the lessons, go through the textbook, and then I can supply some other stuff as we go through. So we were discussing our current electricity, and we've mentioned the term circuit before, but let's talk about how we express them and how we create them. The first thing we're going to talk about is these things called circuit diagrams. They are obviously a practical way to show someone how to make one. A lot easier to draw them on paper, and then you have all of the information that someone would need to create the circuit themselves if they wanted to. So that's why we create these diagrams. But we have some rules when we make them so that everyone uses the same standard, so it's easy to interpret, right? They always have to be a square or rectangle. Mostly rectangle is the key thing. It doesn't matter, but basically all the lines which represent wires, if that's not clear, all the lines in it have to be straight, and therefore you have to have an overall rectangular shape for the circuit. The size doesn't matter too much as long as it's rectangular, which basically just means draw the lines straight. It has to be done neatly. Pencil and a ruler is the best way to go about doing it. If you can draw lines that are pretty straight without using a ruler, no, not the end of the world. Um, it, in a traditional setting, if this were like a test or something, a ruler would be useful, but if you could get away with it, making it look not crazy messy without a ruler, then it would probably be okay. But make sure you get one, so when you're doing these next couple lessons, you'll need a pencil and a ruler as you go through the homework. And then the electrical technician is able to build or service the circuit. So the diagrams we're going to talk about are very simple. They're probably not what you'd see. Sorry, in traditional in like an actual wiring plan that an electrician would use, but there are lots. But circuit diagrams do exist, and they're just more complicated. So we're going to get you used to the rough idea, the basic idea of them, so that if you decide to go into this in your career, then you at least have some familiarity. So a circuit diagram is just strictly defined as a diagram that uses standard symbols to represent the components in the electric circuit and their connections. Do you remember what it says right here, load? So we have straight lines for wires. We'll have a battery, a source of some kind, and then we'll put loads or switches in the circuit, and that's pretty much it. So let's take a look. So we have a bunch of blanks in for all of the types of loads that we will put in, and what we'll do is we'll actually get the pictures from the textbook, and you can fill them in this note. If you've been filling these notes in as you go, I would recommend, I'll show you where it's in the textbook, and then you can fill in the symbols as we go through, and I can also probably create my own. So the sources of electrical energy, we have a couple of classes. We have the conductors, which is just wires. We have control devices, loads, and then these meters are going to be the important symbols that we're going to get. So if we go to the text here on page 457, let me just zoom in. On page 457 down here, we see that we have all of the symbols that we need for those loads. So going to the note, it says electrical conductor. See how it says connecting wire? If we go to the textbook, connecting wire is here. It's just a straight line to draw in there. The switch, open switch versus closed switch. We see a switch in this case. The closed switch is just, this is an open, right? Because this shows it open. A closed switch is just a straight line connecting the two dots. We see that we have a resistor or a load, right? Specifically, resistor looks like this, the sort of jagged line. A battery looks like this, some big lines, followed by a big line followed by a small line. So we have a big line, small line, and that represents actually one cell in the battery. So the fact that we have a big line and a small one and a big line and a small one, so 4 lines total, means that this is a 2-cell battery, right? The individual cell is just composed of one big line and then a small one, right? Big one first, small one second. Notice that the bulb, I find these very difficult to draw. It looks sort of like an M, right? I believe that this is meant to look like the filament inside of a bulb with a circle around it. So we have our cell, we have a 2-cell battery. We can fill in the AC power source in a bit. We know how to do open and close switch, and then we know how to do the resistor, we know the light bulb, and then the 2 meters are the last two. AC source at the bottom, just a little bit of a wavy line in there, and then we have voltmeter and we have ammeter as well, just a V with a circle and A with a circle around it also. So these are the symbols that we're going to be using, and these are the components that we're going to be focusing on. We may add motor in. I can't exactly remember if we have a sheet. You may also have a sheet in you don't have the note package, I'm sorry. So we can add in a few ones, but any additions I will definitely let you know about. But for now, these ones in the text are going to be very, very important, and knowing these symbols is going to be very important also. Okay, let's talk about how we can construct them. There's 2 types of circuits that we're going to talk about. We have a series circuit and we have a parallel circuit. Let's take a look at the series circuit first. Series circuit is a circuit in which there is only one path along which electrons can flow. Here's an example of a series circuit here. We have a 2-cell battery connected to 1, 2, 3 light bulbs with our wires around in a rectangular shape. Notice that we said before, that electrons can only travel in a single direction, one-way street. So they'll start at the battery, they'll go this way, and then they'll turn, go through this bulb, giving off light energy, go through this bulb, go through this bulb, losing energy as it goes through each load, and then completing the circuit and arriving back at the cell or at the battery in order to start the process again. Only one direction for those electrons to go in. So this is called a series circuit. Goes from the negative terminal to the positive terminal. They're called series connections, where all the components are connected. You can picture racing cars on a racetrack, like that analogy I said earlier, right? It's sort of like them just going in a big circle. So here's 3 bulbs. Now this is the interesting consequence of a series circuit, is that since there's only one pathway for electrons to flow through, if there is a break anywhere in this, right? So if there were a switch or if one of these bulbs was unscrewed, the electrons can't travel through anymore. There's sort of like a blockage, right? If there's a blockage, no other component or nothing in the circuit will work. So that's the interesting thing. So this is basically, so if a bulb burns out, right? So this is just like Christmas lights is probably the best analogy of this. I doubt any of you have any experience with this. You probably are too young for this, but this is I am not, unfortunately. And Christmas lights used to, so the lights that you would put on your tree or put up around your house, they used to be wired in series. What that meant was that if I plugged in my Christmas lights in like November, or whatever, when you're putting the Christmas lights up, they've been in the basement for like months. You plug them into the wall and they don't turn on. Does that mean that all the lights are broken? No. You have to go through each individual light, basically unscrewing it, putting in a replacement bulb, and seeing if it works, which can be very cumbersome and tiring considering how many lights that you would have. So it's very difficult to figure out, right? You could maybe look through all the bulbs and inspect, and you might be able to see which one burnt out, so it might actually take you a little less time, but that was what you had to do, right? So if one thing in the circuit doesn't work or basically breaks the pathway for electrons to flow, then electrons can't get to anywhere else, right? If there's an accident on a one-way street and there's nowhere to turn, you are stuck, right? You can't just reverse, right? You can't go around it because you have to drive on the road. So electrons, basically, you can picture that they just get stuck and then they can't through. So if this first bulb burns out, then they can't get through. Now, if this second bulb burns out, you might think, well, wait a minute, sir, doesn't this first guy work? No, nothing works. Even if it's this second bulb, you might say, well, electrons can sort of get through this first one, so don't they give off energy? But they can't get through this second guy. So if you're going to leave your house and then you check your phone and it says, oh, there's a huge accident on the road, are you still going to leave your house and drive just to get stuck? No, you'll just stay at home. That's sort of the analogy here as well. So basically, electrons can sort of get like an idea, and if there's a breakage, then they just don't bother going, and that's why, and that's part of the reason why it's not like if this third bulb were burnt out, you wouldn't see just these two working. Any of them are burnt out, none of them work. All the current goes through all the bulbs, and the more bulbs you add, the lower the current gets, and you can't turn off just one of the loads. It's all or nothing, right? So that's the thing. So if you wire anything in series, it's all or nothing. They all have to be on, they're all working or none of them are working. Let's contrast this now with our parallel circuit. And a parallel circuit is a circuit in which there is more than one path along which electrons can flow. So in this diagram here, we have our 2-cell battery at the bottom, and then, let's just, for consistency, the negative terminal, I guess, I actually forget which one. It doesn't matter too much to me. Negative terminal goes maybe this way up here. We see that there's a branch point now. So if you picture electrons like cars, when it gets to this first point here, it can turn to the right and then continue to complete the circuit, or it can go straight, right? So it has sort of like a choice. So what ends up happening is that some electrons will turn, and then they'll turn again, and then they'll complete that circuit, and then they'll kind of go in this pathway. Whereas others will continue going straight, and then they reach this junction point. And then again, we have another break where some will turn here and then go down and complete that circuit. Whereas the rest go all the way up, and then end of the line where they have to turn, and then come back and complete the circuit. So we basically have these three sort of loops going around with electrons sort of splitting the number of electrons more or less between these three pathways. So this is called a parallel circuit. Also, if it helps picture, notice that there's these lines, right? These wires are all parallel to each other, if that kind of helps maybe, so that you can picture these different branches as coming off in parallel to one another. So electrons, again, they can only go one direction from negative to positive, so that hasn't changed, right? The specific parts of a circuit where there are more than one pathway are called parallel connections, okay? So that when we look at, so these two bulbs, we say, are connected in parallel across this other bulb, because if you take a look, so we have a junction point here and a junction point there, right? Or a connection point. And then if I go up from both of those connection points, I have another bulb, right? So it's like this second bulb here is sort of stacked on top of the first one. And then the same thing with this second one. It's sort of almost stacked on top. Different than our series circuit where they're just one after the other, right? So notice that difference in how they're connected, right? I don't have a pen, sorry. How they're connected. Whereas if I were to connect something in parallel in a series circuit or across, I would add a point here, up, over, and then back down. Hopefully you can sort of see my little motion with my mouse there. Okay, cars driving through a city block, right? This basically looks sort of like a city because there's streets that you can turn on, right? Now, this is the interesting consequence of the parallel circuit. If one of these bulbs burns out, the other two will continue to work. Because if this guy burns out, it means that electrons can't turn right, but they can still go straight and around and get back to the source, right? As long as they can complete a full circuit somehow, then energy can go through there. So in a parallel circuit, I can have even these two bulbs up here burnt out, and I can still see energy through this one. The reason that happens is because there is a pathway from the negative terminal of the power source to the positive terminal, right? Electrons can still flow through. In my series circuit, I can't, right? Because if this bulb is burnt out, I can't go through there, right? So we see a similar blockage. If this bulb and this bulb are burnt out, there is a blockage those ways. But what that means is that electrons don't go that way, and all of them will now go through this open pathway. Hopefully you can see what I'm talking about there, and that will help you understand these, right? So parallel circuit, we can have them burnt out. It's not all or nothing. We can have some bulbs on, some bulbs off, okay? The current is split into parts. Only part of the current goes through each bulb. If more bulbs are added, though, the brightness does not change. The brightness will stay the exact same. So that's a little bit different here. all of the current has to go through these bulbs, right? So we're getting the same current going through all of them. But if we add more bulbs, then we're losing energy as the electrons go through, right? So they're sort of getting more tired the more bulbs we add, so the dimmer they're going to get. Whereas in a parallel circuit, we can add a bunch of bulbs and they'll all have the exact same brightness. It gets sort of split evenly between the three of them. But we notice that we have different amounts of current kind of going through them because we have to split the current in order to go through these three. Most circuits are combinations of series and parallel, right? Parallel, you can see, is very superior. In fact, like all modern Christmas lights are wired in parallel. So if one of your Christmas lights goes out, like just this past Christmas, if you had any bulbs that burnt out, the rest of the bulbs still work. So all you need to do is just find the one burnt out bulb and replace it, which is very easy. So you can still use them, which is nice. Okay, let's talk about measuring current and potential difference in a circuit. So we mentioned this before. We use an ammeter, which measures the current. And remember that the units for amperes, the unit for current is amperes with symbol A at a particular location in a circuit, right? So the ammeter, we have to plug in somewhere in the circuit we can measure the current, right? The ammeter measures the flow of electric charge at the point where the meter is connected. So only in that specific point. So that's sort of the limitation of an ammeter. It has to only be at one point, right? You have to connect an ammeter in series. That's going to be important because we will see that it's the opposite for a voltmeter. So a voltmeter now measures the potential difference, which we said was measured in volts, right, between 2 points in a circuit. So just remember that we said electric potential energy always has to be measured between 2 points. Voltages, same thing, because remember a voltage is basically the same thing. So the voltmeter is connected in parallel across something so that we're actually measuring the energy difference between these 2 points in a circuit, which we say is just the voltage. So we're measuring 2 points, right, whereas the current is only a single point. So the electric potential on one side of the load, like a bulb or a resistor, is greater than the electric on the other side. So remember that the electrons lose a little bit of energy. So basically we're saying, okay, how much energy does the electron have going in and how much does it have going out? And then that tells us the potential difference for that particular load, right? So we can figure out basically how much energy a load uses from that way. So we connect. If I have a picture, I don't think I have a picture. Oh, maybe I do in the text. Sorry, one sec. Okay, the closest example I have, and I might be giving away some of the answers, but I kind of don't care, is if I look at this circuit diagram down here on the bottom of page 461, I see I have a light bulb, I have a battery, and I have a switch, and I have a bunch of wires, and I have some resistors in here. The way that the connection works, to sort of give you an idea, for the ammeter here is connected in series, right? It's connected in series to the kind of main pathway of this circuit, right? The circuit starting with the battery, going to the switch, then going to resistor. Notice how it's like an input-output, right? Just like sort of the thing I showed you with the FET simulation. Oh, in fact, I can actually probably use that. But anyways, input, output, that's it. Same thing for the ammeter. It has an input, it has an output, and then it's connected directly after this resistor, and it goes into this last resistor to the bulb, right? Whereas the voltmeter down here, take a look, it's not sort of in the chain, right? It's off. It's staggered, or it's stacked on top. We see that we have a branch, right? There's 2 inputs going into one side of this resistor, right? One of which goes to the voltmeter and then the other on the other side of the resistor. So this voltmeter is measuring the potential difference across this resistor is what we say. We have, right, input, output. We're basically splitting the path of electrons that goes around. And by doing that, we can measure their energy here and their energy here. And then the voltmeter will give us a reading that says, okay, here's how much energy is lost over here. Whereas the ammeter will give us a reading that will say, okay, this is the amount of current that's passing through. Remember that current will be the same in the series, whereas the voltmeter, depending on where we're measuring, we can see different values there. I can show you another example as we go through. So let's talk about multimeters then. We mentioned that a bit, right? A multimeter can be used as either when it has to be connected in series. When it's connected, it has to be in parallel. So the multimeter has to be in series if it's measuring current, or it has to be in parallel if it's measuring voltage. Then let's talk about electric energy and gravitational energy, which we mentioned before. This is like the waterfall analogy, right? A battery has a bunch of cells that are connected. If you connect cells in series, the positive terminal is connected to the negative of the other one. The potential difference across a battery of cells in series is the sum of the potential differences across each cell. So whatever the voltage, the voltage of the battery is just the sum of the voltage of each individual cell in the battery, right? Which hopefully makes sense. Okay, potential difference that is generated by a cell is limited to a few volts. When a larger potential difference is required, several cells are connected in series to make a battery, right? Okay, yeah, so this is a little interesting point here, and this is one of the questions in the textbook, so this will help you with that. So like a 9-volt battery, right? Typical 9-volt battery is actually made up of 6 small cells, and each of those cells has 1.5 voltage to it, right? So basically 6 times 1.5 gives you 9. So the total voltage of the battery is just the sum of the voltage of the individual cells that are in there, right? Now, you might not know how many cells are made up, but if I tell you the total voltage of a battery, I tell you the number of cells in the battery, you should be able to tell me, just by doing division, what the voltage is of the individual cells, or like any variation of that, right? I could basically give you 2 of these 3 numbers, and you should be able to figure out the missing one. Let's take a look at the homework quickly. You have a learning check on page 458, review questions at the end of the chapter, and then I also have some extra questions here. Notice that I crossed the attached worksheets because we don't have any attached worksheets. So basically, you're going to be doing these questions in here as well as answering these, which is going to be drawing these circuit diagrams. You can draw these circuit diagrams on paper, or I can actually, we can draw these circuit diagrams. How do I want to do this? I need to figure out exactly what I want to do, but you can use a program. If you wanted to create a circuit diagram in PowerPoint or something, I could do a little tutorial on how to do that. And you can also do the simulation that I showed you, PHET, in the physics, and you can make your own circuit by going to the circuit construction kit and starting this. So you can make any of your diagrams in here if you like, and you can just take a screenshot of it, save it as like a JPEG or something, please. That would be helpful. Why don't I show you how to connect the ammeter and voltmeter real quick. So I'll just kind of make a circuit. Okay, so here's my circuit. If I click down here, I should see them. Oh, they're over here, sorry. I have an ammeter and I have a voltmeter over here, right? So I can drag these guys down. How I connect the ammeter, I actually have to kind of break a connection and then insert it, right? So then my wire goes down there, my wire goes over here. And then notice how, okay, things are working fine, the electrons are flowing, the bulb still works. But the ammeter actually has to be inserted into the circuit, right? So this is now in series. The voltmeter is pretty handy because I can actually just use the 2 leads of it like this, right? And then I can get the voltage measured like just by putting it in parallel, right? So while this might not look like it's strictly connected, some voltmeters do require an actual like input, like you might have to do a connection, but I can just do it like this. I don't need to disconnect, right? I could just clip these on to the side of the of this light bulb, right? So it would sort of look like. So the way how it would look to connect something in parallel. Let's say I want to put a light bulb in parallel. So I just connect it very similarly. I branch off one point and then connect it to the other side. So then now we notice that we have electrons moving along this way and then branching over here, right? So we have some electrons are going through this one bulb from here to here and continuing along, whereas others are branching and going up to here and then coming out there and then going back down, right? So this bulb here is now in parallel to this other one. Hopefully you can see how that works, right, the way that we've added it in. Okay, great. That's it for me. Hopefully this was helpful.